Hi, welcome to Reader's Digest version, everyone. Today we're looking at the transformations of sinusoidal functions that we can use to shape these sine and cosine functions to suit our needs. So one of the things that we did while you were gone is we graphed the cosine and sine. So here's a picture of sine, and here's a picture of cosine. And you can watch the video and sketch it yourself. Or if you're good with the unit circle, you can use your unit circles. Here's the unit circle at 30, and there's those values. And we have the unit circle over there. We filled that in as well while you were gone, so you can see the video. But anyway, just that is to say, here is sine, here is cosine. And these are the things we notice about them. And we'll take a look at the cosine curve. Its amplitude, that means the distance from the horizontal axis that it rises or falls, is 1 for both parent functions. So it goes through the point 1 or the point -1 here at its minimum. And we see sine has the same amplitude. That's 1, that's -1, and there's the maximum, there's the minimum. So we could also put the amplitude there. And then, yeah, you can sit in your desk, that'll be a better spot. The period is the length of one cycle. And here we're only showing one cycle. One cycle is 360 degrees. And then the horizontal axis is the midline of the whole function, happens at y equals 0, along the x-axis. Okay? And then the phase shift, that's its Y-intercept and where it starts and is it rising or falling, that's all going to be governed by another transformation. So let's take a look at these things. We want to be able to use f of x is sine x or f of x is cos x and apply transformations to those and then graph the resulting functions. We would also like to be able to look at a function and say, I can predict what transformations I need to do to make the function look like that. So, sure thing. So we remember that this is where we see our transformations. A is multiplying outputs of a function. K is multiplying inputs. D and C are adding on to inputs or adding on to outputs, respectively. And we remember that those are vertical stretch for A, horizontal compression for K, horizontal translation for D, and vertical translation for C. So this is where we see those in the sine and cosine functions. You're going to have this multiplying your output, this multiplying your input, this one being subtracted from your input. Put that in brackets. You can do the algebra here and evaluate it, but it can be a little trickier to work in that way. It's tricky to work in both ways, to be honest. D is going to be the trickiest value to find, I find. It's the least intuitive to get things to line up right. But once you learn the formulas, you'll be able to do it. And then C changes the axis, changes the vertical position. So we notice that these functions here, we have y is equal to 2 sine x there. Y is equal to sine x is the black one, so that has the amplitude 1. And y equals 2 sine x, well, that has amplitude 2. And these are A transformations. So these are multiplying the output. And here is a y is equal to 1/2 sine x, and it has half the amplitude. So not only does the A value affect the maximum and the minimum, but it affects the amplitude of these functions. Another thing to remember, notice that the x-intercepts, they stretch to themselves. They don't stretch. Because multiplying 0 is just still 0. So that's why those are still there. Okay. So then we looked at some questions like, if I told you that f of x is equal to 4 multiplied by sine x, what's the amplitude of that? You just read it. It's just the A value. It's just 4. Okay. So I gave you some trickier ones, I think, on the handout. So let's take a look at one of those.
If nothing's in front of it, is it 1?
Yeah, that's right. It's a cheeky one. It's like I'm 41 times 1 years old. So 15 sine x, what will the amplitude of 15 sine x be?
Where are you looking?
15. Yeah, it's hard to make a tricky question there. So that's going to stretch it just down here. And then we can flip that page over to look at now the K transformation. K is also tricky. D and K are always tricky, right? They're weird sign flippers, or K divides instead of multiplies like you'd expect with A. So we can expect some trickiness here. K is determining the period of these functions. So if we have large values of K, it effectively squeezes the spring towards the y-axis, so you finish a period across less x. Imagine x is time. and in 10 seconds you want this function to go through one full cycle, for example, we can create trigonometric functions that will do that. So let's take a look at some. Here's Desmos, and we have some ugly functions there. Let's turn them off. And we're going to take a look at how this k value affects this function here. So this is 3 multiplied by cos x. And if I zoom out to show you a full period, I need to show you right now all the way up to 360. So there is a 360 degrees, but it could also be 360 seconds. Let's say it's a Ferris wheel where you start at the top for some reason, and then it goes 3 meters underground after 180 seconds, and then takes you 3 meters above ground. See, this is a weird Ferris wheel, right? So maybe I'm like, well, I don't like that Ferris wheel. I would rather be up in the air that much. I like that Ferris wheel better because I get a better view from up there. That would make more sense. Okay, so that's going through one period in 360 seconds. But that's 6 minutes. That's a really boring Ferris wheel. Let's make it a more interesting Ferris wheel. Let's go around one time every minute. So now we want a period of 60. So actually I want this to go around 6 times faster. So if I put a 6 there, notice that it gets through one period after 60 seconds. Okay. Now how do we do this? How do we interpret these values of k? Well, let's take a look at some formulas. The formulas are k is equal to 360 over the period. So I wanted a period of 60 seconds. So in my mental arithmetic brain, I put 360 over 60, and that output 6. Okay? So I knew that 360 over 60 would give me a value 6, so I had to put 6 into the function. That way, when I input the value 60 as x, it would be 60 times 6, which would be 360. So it tells me, okay, I've gone through one full cycle. This is why k is doing that. Okay? I can also use the reverse of this, where I multiply both sides by the period and divide both sides by k. This formula here, if I want to look at a function and say, what is its period? So if we have a function like sine is 2x, well, I use that formula. I say the period is going to be 360 divided by 2. The period would be 180 for that function. So these are the two formulas that you can use either to find k, given you want the period to be something. Let's say we want the Ferris wheel to be even faster. So I'm going to take this Ferris wheel here, and I'm going to, instead of 6, I'm going to do 12. And now it's twice as fast. Now it's every 30 seconds it goes around. Because 360 divided by 12 gives me 30. So 30 will be the new period.
So is it the larger the period, the shorter the time or something?
Well, it's all, so the longer the period gets, the smaller k is. And k is just a number that we use to squeeze these functions so that we can get them to match our data, or we can get them to match the situation we're trying to create or a graph we're trying to emulate. Okay, so those are those. Now the k value, another hint, this is a way you can think about it, Rylan, is the k value tells you how many cycles you'll see within 360 degrees. So let's take a look at the example we were just looking at. Here we go. If we count them, this is one full cycle here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12 is just on the edge of the screen there. That's the point 360. You see there, 360. And so we went through 12 full periods across 360x when k was 12. So it tells you how many bumps are going to be within the value 360. Okay. And then moving on, we now look at d values. So d, horizontal translation. Takes the whole shape, doesn't change the shape the way k does or the way a does, but just shifts the shape to the left or right. So this is called phase shift. It creates, it just moves all the mountains that way and all the valleys that way, or moves all the mountains this way and all the valleys this way. And to work with d, if we're going to take a look at like what's the phase shift and the Y-intercept in each of these following cases, these can be, I think, the trickiest problems that we're going to have here, is finding that right D value. And let's take a look at how we can think about these and understand these. If we have f of x is equal to sine x as our parent function, and we just sketch that, it's going to look like this. So it's going to, hold on one second. Okay, so let's keep going with our Reader's Digest version here. So let's sketch a sine x over 360. It's going to come up, go down, and then come up again. Okay, and this is 90 here. This is 270. And this is 360 there. So if we do x plus 45, it's going to take this whole thing and shift it in the negative direction 45. So it's going to take this point that's over here at 45 and move that to be the new y-intercept there. Okay. So this is this is a phase shift of negative 45 because this is a weird sign flipper, and the y-intercept is going to be 1 over root 2. Why is that 1 over root 2? Because remember your sine for 45 degrees is opposite over hypotenuse, 45 degrees. Right? Let's take a look at it. Sine of x plus 45 in Desmos. If we were looking at this one, we're just going to turn this into a sine wave here. That's just a normal sine wave. I think it was more efficient by far to write it myself. But anyway, there we go. And I'm predicting that this point, 45, 0.707 is 1 over root 2. So there it is, 45 degrees. I predict that will be the new y-intercept when I say sine of x minus 45. Oh, where did it go? Where did it go? What happened? Why isn't it still there? Oh, right, because that's a C transformation, Mr. Jennings. You need to put that in brackets. Oh, and it was plus 45, not minus 45. Plus 45. There. So now look, there it is. There's our 1 over root 2. That's our new y-intercept. And it happened by pulling the whole function that way. Okay. Let's take a look at the next one, which is cosine of x minus 30. So again, visualize your function. We have it drawn out nicely over here. So let's take a look at it. If we had this move this direction by 30 degrees, well, the continuation of this function on this side looks like this, right? It's going to be level, symmetrical with that. That's the point negative 30 degrees there, or it's the same thing as 330 degrees there, because this is happening over here as well, because it's a mirror. And if we subtract 30 from our inputs, that's going to effectively move the whole function to the right in the positive direction by 30 degrees. So this will be root 3 over 2, because this point here for these angles here is root 3 over 2. So let's take a look at that. So now we're going to change this one to cosine of x minus 30 now. And there it is. See, this used to be the y-intercept, but it was moved 30 points that way. And now the new one is 0.866. That's root 3 over 2. So there it is. So that's how our phase shift works. And now, let's take a look. No, that's the wrong spot. That's the wrong spot. Here. So the last thing to look at is the C value. The C value just moves the axis. Moves the whole thing up and down. It is going to change the maximums and minimums, but it does not change the amplitude. Just takes the whole amplitude and moves it up or down. And then we can take a look at like things like sine x plus 2. Well, that has an equation of an axis of y equals 2. Cos x minus 3, that has an axis of y is equal to minus 3. And yeah, domain and range, we're not going to talk about domain and range. So then we looked at this example as a class. And I want to talk about this example with you before I say, give it a try. Go try some of these things. So if you take a look at this example on your sheet here, is this example. And I will get us a clean copy of it so we can start from a clean copy. So just give me a second. So when you look at this function here, what's the period of that function? 4, right. So you can find it in many different ways. You just need to find the same point in 2 spots, and then that's your period. You can't, but you have to be rising or falling. You have to be both rising or both falling. Like you can't say, well, here it's at 2, and there it's at 2, so that has a period 2. No, because here it's falling and here it's rising. That's not one full cycle. You would have to say this falling 2 and that falling 2 are separated by 4. Okay, so the rising and the falling also matters. So this has period 4. What's the amplitude? Yes, because the distance between 5 and -1 is 6, and half of 6 is the amplitude, so 3. Yeah. And what's the equation of the axis here? Well, we want to find the midpoint of the function. So visually it's there. See that visually? But then the way you find it is you just average 5 and -1. So 5 plus -1 divided by 2, 4 divided by 2 is 2. So that's how we find the equation of the axis, is there at 2. And then we have just about everything we need to start putting this together, especially if we're using cosine. So let's start with cosine. Okay. First of all, we need to use the period to calculate our k value. So remember, we have a formula for that. It's k is equal to 360 divided by the period. So what's our k value? What's that? 360 divided by 4. Think of a pizza as 360 degrees. What's a quarter? 90, yeah. So you don't even need to do your arithmetic now. You can just think of 360 and think a quarter of 360 is 90. And that's very fast. It's 90. So we want a k value of 90. Amplitude is 3. So this gives us our k. What will this amplitude determine in terms of the transformations? Yeah. So that's going to be an a of 3. And how about this axis of 2? Yeah, that's going to be our c. So c equals 2. Very good. So we've got 3 of the 4 numbers we need. Now we need to figure out d. If we're looking at cosine, how much has that been shifted to the left or right if we're cosine? If we take a look at our cosine function here, it seems to have a y-intercept that's already its maximum. This function here has a y-intercept that's also its maximum. So has it been shifted to the left or right? No. So d is just 0. Yeah. So we can create a cosine function for this, and it would look like f of x equals 3 multiplied by cosine of 90x plus 2. Let's graph it in a fresh Desmos and see if we get something that looks exactly like this. So here is I'm just going to get a fresh Desmos here. Reload. I know I want to see numbers like this, so that's fine. And I'm going to have f of x is equal to 3 multiplied by cosine 90x plus 2. Uh-oh. Did we make a mistake somewhere? How is it so big? No, it's not that. It's that this is in radians. You need to flip it to degrees. Dun, 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 dun. There we go. Okay. So just a little joke there. Yeah.
Wait, so what did that give us? The transformation of z.
Oh, so that gave us this. When we flipped it to degrees?
No, like, what is the f of x that we just did? Like, what was that for?
Oh, that's to find a function that matches that graph.
Oh.
And here is the graph of that graph. That is that function. So we were correct. When we evaluated the amplitude, we found the horizontal axis, and we saw we didn't need any phase shift. But if we want to use sine for this, we'll see that we need some phase shift. Notice that if I want to create a function with sine, Sine starts at its midpoint and then starts rising. But I want this to start at the maximum. So how can I get that to work and start that at its maximum? There's actually an infinite number of correct answers for D here.
What was the question?
What value of D do I need to add or subtract to my X values to get this to go, to get this to work? Yeah. Which one? Which flavor of one? Yes. X plus 1 will do it, because when we're looking at this function here, Faith notices that she can pull this point that way with a positive D of 1, and that will do it. We could also take this one over here, 5. And it's going to be equivalent, absolutely equivalent, X plus 5. We could also do X minus 3, or X minus 7, or X minus 11. See where I get all these different D values? And they'll all translate the function so that it's starting at its maximum and going along. The simplest one would be plus 1 that you gave me. It's great. That's the one you'd want to use. So yeah, those are how you tune your functions and make them match what you want them to be. That way you can now start working in word problems and solving word problems, or looking at trigonometric functions and analyzing them, etc., etc. Sorry? A? So let's try a different value of A. Let's try 5. Whoop. It just changes the amplitude. So a lot of times with a lot of these questions, and I'll go back to my terrifying trigonometry over here. Let's turn on the Ferris wheel. So here's my Ferris wheel, and I'm going to unrotate it. So there we go. And I'm going to take away some of the busyness by turning off some of these sinusoidal functions and just zoom in here on the Ferris wheel. Notice that the Ferris wheel here, I made it fit in the unit circle. So it has a radius 1, this Ferris wheel. And it's also half underground if you assume that the x-axis is the line of the ground. But I did it that way for reasons. So now if I highlight this point that's U, and I say you are going to rotate around the Ferris wheel here, and I say, well, I want to model your vertical displacement, and that's what this is showing me, my vertical displacement here, right? And then I say, well, show me that as a trigonometric function. There it is there, but I have to animate that so that it starts there. See how that's going to follow this point? And that's my trigonometric function that would model this behavior. Notice this is a trigonometric function, and it has the same amplitude as the radius of this Ferris wheel. The radius is 1, so the amplitude of the trigonometric function that matches that would be 1. The midpoint of the Ferris wheel is at 0, so its horizontal axis is also 0. I set it up that way because I didn't do the natural thing of making the ground 0. I made the axis 0, but you could do that. And then its phase shift, well, let's not talk about its phase shift and things like that. I have the phase shift changing constantly so that it matches that there. So yeah, those are the skills that I want you to have. So that's the Reader's Digest version. So thank you for tuning in with us.